How big is the observable universe? It's a question that immediately stirs both curiosity and wonder, because it touches the very edges of what humanity can comprehend. When we look at the night sky, those tiny points of light represent only a minuscule fraction of the cosmic ocean around us. Modern science has given us tools to peer deeper than our eyes alone could ever manage, but even with the best telescopes, there is a boundary beyond which we cannot see. That boundary is what we call the observable universe. And within that idea lies a paradox. We live inside a universe so staggeringly vast that even the part we can observe defies comprehension, while beyond that horizon, there may be far more than we could ever imagine. This single question, how big is the observable universe, is not just about measuring space, but about probing the limits of time, matter, and human knowledge itself. When we ask how big the observable universe is, the very word observable becomes the cornerstone of our exploration. It is not a casual word. It has a very precise meaning in cosmology. To call something observable means it is within the realm of detection, that light or other signals from that region have had enough time to travel across the gulf of space and reach us. Because light is our main cosmic messenger, the observable universe is essentially defined by the distance light has been able to cover since the beginning of the universe. This isn't just a matter of where things exist right now. It's about where light has had the opportunity to reach us during the entire lifespan of the cosmos. To truly understand this, imagine the universe as a vast ocean and ourselves as tiny observers floating on a small raft in the middle. The ocean may extend endlessly in all directions, but we can only see the part that lies above the horizon. The horizon, in this case, isn't a physical wall, but a limit created by the curvature of space-time and the finite speed of light. Anything beyond that horizon is still real. It still exists, but its light has not yet arrived at our raft. Thus, our observable universe is a cosmic horizon shaped not by what is out there, but by what has reached us. The word observable also points to the fact that we are not measuring the universe itself directly, but our perception of it. There may be galaxies, stars, and whole clusters beyond our horizon, but because their light is still traveling toward us, we are unaware of them. That doesn't mean they don't exist. It simply means they lie beyond the boundary of observation. This is a critical distinction because many people hear observable universe and mistake it for the universe. The truth is far more staggering. The observable universe is merely a portion, a slice, a bubble we inhabit, surrounded by a far larger cosmic reality. This concept becomes even more powerful when we realize it's not just limited to Earth. Every observer, no matter where they are in the cosmos, has their own observable universe, defined by the light that has reached them. An alien civilization, billions of light years away, would have its own horizon, overlapping with ours in some areas, but stretching into regions we will never see. The observable universe, then, is deeply personal to each point in space, like bubbles in an endless foam of cosmic perspectives. This means the universe doesn't just have one edge, it has countless edges, all relative to where the observer stands. The importance of observable also highlights the nature of scientific humility. What we see is always constrained by physical laws. The observable universe is not a snapshot of all that exists, but only what we can gather with our tools and our position in time. It is, in a way, like looking through a foggy window. The fog doesn't mean there's nothing outside. It means our view is limited by conditions beyond our control. For cosmologists, this limit is not discouraging, but rather thrilling, because it invites us to wonder, if this is only what's visible, how much greater is the invisible? Furthermore, the observable limit changes over time. As the universe ages, light from farther regions has more time to reach us, so the boundary of what's observable expands. In the distant future, if intelligent beings still exist, they will live within a larger observable universe than we see today. Conversely, if we could somehow rewind to billions of years in the past, the observable universe would have been much smaller, because less light would have had time to travel across the cosmos. This fluidity shows that the concept of observable is not fixed, but tied intimately to time's passage and the journey of light. It's also worth emphasizing that the observable universe doesn't mean we can see everything within that boundary clearly. Light may have reached us, but it may also be too faint to detect with current technology. Some regions are obscured by cosmic dust or drowned out by brighter objects. This means that while the observable universe defines the maximum extent of visibility, our practical observations are often smaller and patchier. Still, with instruments like the Hubble Space Telescope and the James Webb Space Telescope, humanity has stretched the reach of observation to remarkable limits, pushing deeper into this observable frontier than ever before. To tie this back to the original question, the size of the observable universe is not just about distance, it is about time, light, and relativity. The boundary is a horizon of knowledge, carved by the finite speed of light and the finite age of the universe. The term observable does not constrain the cosmos, it constrains us. It tells us what has had the chance to announce its existence to our eyes and instruments. And it serves as a humbling reminder. The universe is far larger than what we can perceive. The observable part is just our small window in an ocean of immensity. The journey toward answering how big is the observable universe thus begins with understanding this very word. Without the concept of observable, the question loses its meaning because we would be trying to measure the immeasurable. But once we define it clearly, we gain a framework, a cosmic horizon, that allows us to ask meaningful questions and make extraordinary discoveries. And at the core of that framework lies another crucial concept, the speed of light, the ultimate governor of what enters our observable world. The notion of the observable universe is inseparable from one of the most fundamental laws of physics, the speed of light. Light is not merely a convenient unit for cosmic measurements, it is the ultimate speed limit of the universe itself. At approximately 299,792 kilometers per second, or about 186,000 miles per second, light zips through the vacuum of space faster than anything else we know. Yet, despite this staggering speed, when it comes to the scale of the cosmos, even light is surprisingly slow. This is why the universe has a visible horizon at all. If light could move infinitely fast, we would, in theory, be able to see everything that exists instantly. But because it moves at a finite rate, our view is restricted by how far light has managed to travel since the universe began. The speed of light is not just fast, it's absolute. According to Einstein's theory of relativity, nothing can move through space faster than light in a vacuum. This means that photons, the particles of light, are the ultimate messengers of cosmic information. Every star we see, every galaxy captured in telescope images, and even the faint afterglow of the Big Bang itself is carried to us by photons traveling across unfathomable distances. In fact, every time you gaze at the night sky, you are seeing not the present state of the cosmos, but a delayed broadcast. The stars overhead may look eternal and fixed, but many of them have already changed, exploded, or even vanished. Their light is simply still on its way toward us. This cosmic speed limit is also the reason why time and space are so intertwined. Because light defines the fastest possible means of communication, distance in the universe is often measured in light years. The distance light travels in a year, about 9.46 trillion kilometers, 5.88 trillion miles. When we say a galaxy is 2 million light-years away, such as our neighbor Andromeda, what we mean is that the light from that galaxy has taken 2 million years to reach us. Thus, to look out into space is to look back in time. Every object we see is seen as it was when its light began its journey. The farther away something is, the further back into history we are peering. This realization is deeply profound. It means our telescopes are not just powerful cameras, but time machines. When scientists aim the Hubble or James Webb Space Telescope at distant galaxies, they are literally peering billions of years into the past, capturing the faint glow of stars and structures that formed shortly after the Big Bang. The speed of light creates this strange but beautiful limit. Our universe reveals itself only gradually, and only in the form of ancient snapshots, carried on beams of light. Now, why does this matter for the observable universe? Because the finite speed of light sets the ultimate boundary of what we can see. The universe is about 13.8 billion years old, so you might assume that the farthest we could ever see would be 13.8 billion light-years away, the maximum distance light could have traveled since the beginning of time. That's the intuitive, naive answer. But as we'll see later, the real picture is far stranger and larger, thanks to cosmic expansion. Still, without understanding the speed of light, none of this would make sense. because it is the foundation that shapes the cosmic horizon. The speed of light also highlights the relativity of cosmic communication. Imagine sending a radio signal to a star system 100 light-years away. That message would take 100 years to arrive, and if anyone responded immediately, their reply would take another 100 years to get back to us. In total, a simple two-way hello would take 200 years. This isn't just a technological limitation, it's a law of the universe. No matter how advanced a civilization becomes, they cannot escape the barrier set by light's speed. And this has enormous implications not only for science fiction, dreams of interstellar travel, but also for our understanding of cosmic scale. It's worth noting, too, that light doesn't always travel freely. It can be absorbed, bent, or scattered by cosmic objects. Gravity itself can warp light's path, a phenomenon known as gravitational lensing, which allows us to see galaxies that would otherwise remain hidden behind closer objects. But no matter how it bends or interacts, light's maximum speed remains the same. This constancy is what makes the observable universe calculable at all. It gives us a reliable ruler for measuring cosmic distances. And so, when we tie together the meaning of observable with the speed of light, we get a clear picture of why there's a boundary at all. The speed of light ensures that we are forever limited to a cosmic horizon, a moving shell of visibility that grows as time passes, but can never extend infinitely. Beyond that horizon, the universe may continue endlessly, but it will remain hidden to us unless time itself allows its light to finally arrive. Thus, the speed of light is more than just a number. It is the law that structures our experience of reality. It is the reason why the universe has a visible edge, why astronomy is always an act of looking back in time, and why we can speak meaningfully about the size of the observable cosmos. And with this understanding in hand, we now turn to the next vital piece of the puzzle, the age of the universe itself, which sets the ultimate baseline for how far light has had time to travel. The speed of light defines the ultimate boundary for how far we can see, but to know how much ground light has had the chance to cover, we need one more crucial piece of information, the age of the universe itself. After all, if the cosmos had existed forever, light from infinitely far away would have had infinite time to reach us, and there would be no observable limit. But the universe does not stretch back forever. It has a beginning, a specific moment in time when everything we know burst into existence. That beginning, according to the best evidence we have, was about 13.8 billion years ago. This number is not plucked from thin air. It is the result of decades of careful measurement, observation, and cross-checking by cosmologists. The age of the universe has been pinned down primarily through studies of the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang, as well as through measurements of the rate of cosmic expansion, known as the Hubble constant. Missions like WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck satellite have given us unprecedented precision, allowing scientists to refine the universe's age down to an uncertainty of just a few tens of millions of years. An astonishing feat, given the immense timescales involved. Why does the age of the universe matter so much for the observable horizon? Because it sets the maximum time light has had to travel. If the universe is 13.8 billion years old, then the farthest any photon could possibly have journeyed is 13.8 billion light-years. That number, on first glance, seems like a natural limit on the size of the observable universe. It feels almost poetic, a one-to-one relationship between the universe's age and its radius. But, as we'll see, the reality is much stranger. Still, before we complicate things with cosmic expansion, it's worth dwelling on the significance of that 13.8 billion year timescale. It is, in a way, the ultimate cosmic clock. Every galaxy we see, every cluster of stars, every swirling nebula, all of it has had no more than 13.8 billion years to exist and evolve. When we look at the most distant galaxies visible to our telescopes, we are seeing them as they were billions of years ago, when the universe was young and just beginning to form stars. The sheer vastness of time compresses into every point of light in the night sky. Another fascinating implication is that the universe's age defines not just the reach of light, but also the reach of causality. Nothing in the universe could possibly have influenced us from farther away than the distance light has traveled since the beginning. This boundary is known as the cosmological horizon. Anything beyond it is causally disconnected from us. We cannot see it, interact with it, or be influenced by it in any way because its light hasn't had time to arrive. This horizon is what makes the observable universe a meaningful concept rather than just a poetic phrase. What's particularly humbling is how this age puts our human timescales into perspective. Human civilization has existed for only a few thousand years, a blink compared to billions. Earth itself formed about 4.5 billion years ago, already ancient by our standards, but still only about a third the age of the cosmos. Dinosaurs walked the Earth less than 100 million years ago, a number that feels colossal, but in the grand scheme of things is less than 1% of the universe's lifespan. When we say the universe is 13.8 billion years old, we are invoking a timescale so vast that human history dissolves into near nothingness. And yet, somehow, in this fleeting instant of cosmic time, humanity has managed to measure and comprehend the universe's age. The number also gives structure to cosmology. Theories of galaxy formation, star life cycles, and cosmic evolution all depend on knowing how long the universe has been unfolding. For instance, we know the oldest stars must be younger than 13.8 billion years because they couldn't have formed before the universe existed. Observations of globular clusters, the CMB, and the oldest galaxies all provide checks on this number, and remarkably, they all converge near the same value. This convergence is one of the greatest triumphs of modern science, showing that our understanding of cosmic history is not only plausible, but precise. Of course, there's a twist. If light has had 13.8 billion years to travel, you might think the edge of the observable universe is simply 13.8 billion light-years away. That would be the straightforward assumption, and it seems to make intuitive sense. But this is where the story gets fascinating, because space itself does not remain still. Since the moment of the Big Bang, the universe has been expanding, carrying galaxies farther and farther apart. This expansion means that those regions of space from which the oldest light has just reached us are now much farther away than 13.8 billion light-years. In fact, they are tens of billions of light-years away. Thus, while the age of the universe provides the baseline for how far we can look, it does not give us the whole answer. It is the first step, the ticking of the cosmic clock that sets the stage for the observable horizon. But to fully grasp why the observable universe is so much larger than 13.8 billion light-years, we must turn to another key concept, the idea of look-back time, the realization that when we look across space, we are simultaneously looking back into the deep history of the universe itself. When we talk about gazing deep into the universe, it's tempting to think of it as simply looking at things that are very far away. But in truth, astronomy is not just about distance, it is about time. This is where the concept of look-back time becomes essential. Look-back time refers to the fact that because light travels at a finite speed, the farther into space we look, the further back into the past we are actually peering. Every telescope, every photon, every cosmic image is a time capsule. We are not just observing distant places, we are observing ancient moments in history. This connection between space and time is profound. Take the sun, for example. It sits about 150 million kilometers away, and light from its surface takes roughly 8 minutes to reach Earth. That means when you step outside and feel the sun's warmth, you are feeling energy released from its surface 8 minutes earlier. If the sun were to suddenly vanish, a horrifying thought, it would take us 8 minutes to notice. This is look-back time in action on a familiar scale. Now expand that principle outward to the stars. The light from Alpha Centauri, the closest star system beyond our sun, takes about 4.3 years to reach us. So when we look at Alpha Centauri tonight, we are not seeing it as it exists right now, but as it was 4.3 years ago. Push further, and the effect grows more astonishing. The Andromeda Galaxy, our nearest galactic neighbor, is about 2.5 million light-years away. That means the light reaching our eyes tonight left Andromeda when early humans were first learning to use simple tools on Earth. In every deep sky photograph, the galaxies are not just remote, they are ancient. The farther away they are, the older their light is, and the younger the universe was when that light began its journey. To look across the cosmos is to trace back the universe's own autobiography. What makes this concept even more extraordinary is that look-back time allows us to see the universe's past stages directly. We don't have to guess what galaxies looked like billions of years ago. We can literally observe them because their light is only reaching us now. Telescopes like the James Webb Space Telescope are essentially time machines. They are powerful not because they see the future, but because they can catch light that has been traveling for over 13 billion years, showing us the earliest galaxies that ever formed. In those faint smudges of light, we are witnessing the dawn of cosmic history. Look-back time also highlights a crucial distinction. Space and time are inseparable. When we say a galaxy is, for example, 10 billion light-years away, that number is not just describing distance, it is describing time elapsed. We are seeing that galaxy as it was 10 billion years ago. Today, at this very moment, that same galaxy exists in a much older state, far more evolved, and almost certainly much farther away than where we perceive it to be. We are seeing its ghost image from the past, while its present reality is hidden beyond our reach. This means that the deeper we peer into the cosmos, the younger everything looks. The nearby universe shows us mature galaxies, sprawling with billions of stars and complex structures. But as we look farther away, we see galaxies that are smaller, bluer, and less developed because they existed when the universe itself was still young. Eventually, when we push as far as we can, we reach the edge of visibility, the cosmic microwave background, the afterglow of the Big Bang itself. That is the furthest look-back time we can access, about 13.8 billion years into the past, to the very dawn of time. This also illustrates why astronomy is unlike any other field of science. A biologist, for example, can study life as it is now. A geologist can study the Earth's history by examining rocks and fossils. But an astronomer doesn't just study what is. It is impossible for them to do so. Instead, they are forever studying what was. Every measurement is an archive, a record frozen in photons that have traveled for unimaginable spans of time. When scientists speak of observing the early universe, they are not engaging in metaphor. They are literally looking at it. But here lies a subtlety. Look-back time is not the same as distance. When we say a galaxy is 13 billion light-years away in look-back time, we mean its light has traveled for 13 billion years before reaching us. However, because the universe has been expanding during all that time, the galaxy's current distance is much greater. Tens of billions of light-years away today. Look-back time tells us how old the light is, not where the galaxy is now. This distinction is critical, and it sets the stage for understanding why the observable universe is so much larger than the universe's age might suggest. And so, when we combine the finite speed of light, the 13.8 billion year age of the cosmos, and the concept of look-back time, we arrive at a breathtaking realization. To look into space is to peer directly into history. Every star is a page, every galaxy a chapter, and the universe itself is a library of light. This idea transforms the night sky from a static canvas into a dynamic record of time, stretching back to the very beginning. Yet, if the universe is 13.8 billion years old, does that mean the observable universe is only 13.8 billion light-years across? That seems like the obvious answer, but as we'll soon uncover, the reality is far more surprising. Given the finite speed of light and the 13.8 billion year age of the universe, the simplest and most intuitive conclusion is this. The edge of the observable universe should be 13.8 billion light-years away. At first glance, this seems perfectly logical. Light travels 1 light-year per year, the universe has existed for 13.8 billion years, so the farthest light we can possibly see must come from a distance of 13.8 billion light-years. Multiply that by 2 to account for opposite directions, and you might assume the diameter of the observable universe is about 27.6 billion light-years across. For many people, this feels like a neat, satisfying answer. This is what we might call the naive estimate, and it's not wrong as a starting point. It sets the baseline for understanding why the observable universe is finite in the first place. After all, if the cosmos had existed forever, light could have traveled infinitely, and there would be no observable limit. The fact that the universe has a definite age immediately imposes a ceiling on how far back we can see. It tells us that the observable universe is not an infinite canvas, but a finite horizon bounded by time itself. In a way, this is already astonishing, that the universe has a limit at all, and that this limit can be calculated. If we pause here, the picture seems elegant. A universe 13.8 billion years old, with the oldest light streaming in from 13.8 billion light-years away. But this simplicity is deceptive. It assumes that the universe has remained static over time. that distances have stayed constant, that light has crossed a rigid backdrop of space. In reality, the universe is anything but static. The naive estimate collapses under the weight of one monumental discovery. The universe has been expanding ever since the Big Bang. Still, the 13.8 billion light-year estimate is important to understand, because it represents our first instinct. It's how most people naturally think about the problem before learning about cosmic expansion. Even some early cosmologists initially framed the size of the universe this way, before the deeper implications of relativity and observational data revealed a much larger story. In fact, many students and curious thinkers still stop here and imagine the universe as a giant bubble about 27.6 billion light-years across, forgetting that the fabric of space itself does not remain fixed. The value of this naive picture is that it provides a mental stepping stone. It makes sense to think of light racing across a static void for 13.8 billion years and reaching us today. But when we layer in what we know about cosmology, the fact that space itself stretches and grows, we realize the observable universe must be far larger. Those photons that began their journey billions of years ago did not simply travel through a frozen, unchanging cosmos. Instead, they moved through a universe that was continuously expanding, meaning the galaxies that emitted them have been carried farther away over time. This is why the naive estimate, while intuitive, severely underestimates the true scale of the observable universe. It gives us a radius of 13.8 billion light-years, when the reality, as we'll soon explore, is closer to 46.5 billion light-years. That's more than 3 times greater than the straightforward calculation suggests. But before we leap to that staggering conclusion, it's important to understand exactly why the naive view doesn't work. If the universe were static, then 13.8 billion light-years would indeed be the maximum limit. The problem is that the cosmos is dynamic, fluid, and expanding on a scale almost beyond comprehension. To understand the true size of the observable universe, we must shift from thinking of galaxies flying through a fixed space to realizing that space itself is stretching. Thus, the 13.8 billion light-year estimate is not so much wrong as it is incomplete. It is the training wheels of cosmological thought, a first step toward grasping the observable horizon, but one that must be abandoned for the deeper truth. And so, to go beyond this naive calculation, we must introduce one of the most profound and counterintuitive ideas in modern physics, the expansion of the universe itself, a discovery that forever changed our understanding of cosmic scale. The estimate of a 13.8 billion light-year observable universe feels tidy, but it leaves out one of the most extraordinary features of our cosmos. The universe is expanding. This idea, now a cornerstone of modern cosmology, transforms how we think about distance, time, and the very fabric of space. To grasp why the observable universe is much larger than 13.8 billion light-years, we need to step into the world of cosmic expansion, a phenomenon first uncovered less than a century ago, and one that continues to redefine our place in the cosmos. The story begins in the early 20th century. Until then, many scientists, including Albert Einstein himself, assumed the universe was static, eternal, and unchanging on the grandest scales. That seemed reasonable at the time. After all, the stars in the sky looked fixed and eternal. But then came a seismic shift in our understanding, thanks largely to the work of Edwin Hubble. In 1929, Hubble made a groundbreaking observation. Distant galaxies are not just scattered randomly through space, they are moving away from us, and the farther away a galaxy is, the faster it seems to be receding. This discovery was monumental. It meant the universe is not static at all, it is expanding. Every galaxy, on large enough scales, is being carried apart from every other by the stretching of space itself. The analogy often used is that of a balloon being inflated, with dots on its surface representing galaxies. As the balloon expands, every dot moves away from every other dot, not because the dots are traveling across the surface, but because the surface itself is stretching. Similarly, galaxies are not flying through a fixed cosmic void. They are embedded in space itself, and space is growing larger. This realization was the smoking gun for the Big Bang theory. If the universe is expanding now, it must have been smaller in the past. Run the clock backward, and you eventually reach a moment when all of space, time, matter, and energy were compressed into an unimaginably hot and dense state. That moment, about 13.8 billion years ago, is what we call the Big Bang. The expansion we see today is not the explosion of matter into empty space. It is the expansion of space itself, carrying galaxies along for the ride. The expansion of the universe has profound consequences for the question of how big the observable universe is. Remember those photons that have been traveling toward us for billions of years? They were emitted when the universe was much smaller and denser. But as those photons made their way across the cosmos, the very fabric of space stretched beneath them. This means that the galaxies which emitted that light are now much farther away than the distance the photons themselves have traveled. In other words, while the light has been traveling for 13.8 billion years, the source of that light is now roughly 46.5 billion light-years away. This is the crucial reason why the observable universe is not simply 13.8 billion light-years in radius. Cosmic expansion means that distances grow as light journeys across space. The farther back we look, the more dramatic the effect becomes. A photon emitted just 500 million years after the Big Bang has spent over 13 billion years traveling to us. But the galaxy it came from has been carried outward by expansion and is now many times farther away than its look-back distance would suggest. Cosmic expansion also reshaped how scientists thought about the universe's fate. If galaxies are moving apart now, what does that mean for the future? Will the universe continue expanding forever, or will gravity eventually slow and reverse the expansion, leading to a big crunch? For decades, this question fueled debate. But in the late 1990s, observations of distant supernovae delivered yet another surprise. The expansion is not slowing down. It is accelerating. Some mysterious force, now called dark energy, is pushing the universe apart faster and faster. This discovery added another layer of complexity, but it reinforced the idea that cosmic expansion is the dominant factor in shaping the observable universe's true size. The implications of an expanding universe extend far beyond mere numbers. It alters how we think about reality itself. Unlike in a static universe, there is no fixed edge in the traditional sense, no wall we can point to and say, that's where the universe stops. Instead, the observable boundary is defined by time, light, and expansion, a moving horizon that depends on our position in cosmic history. Future observers, billions of years from now, will have a different observable universe than we do, shaped by how far light has traveled since their own point in time. To truly appreciate expansion, it helps to visualize how it works. Consider again the balloon analogy. From the perspective of any single dot on the balloon, every other dot is moving away, with distant dots receding faster. This matches precisely what Hubble observed with galaxies. But here's the key. There is no central point of expansion on the balloon's surface. Expansion happens everywhere, uniformly. Likewise, in our universe, there is no center, no privileged point from which everything is spreading. Every galaxy sees the others receding, and every observer has their own expanding horizon. This universality is one of the most counterintuitive features of expansion. When we say galaxies are moving away, it doesn't mean we are at the center of the universe. It means everywhere is the center, because expansion is not about motion through space, but about the growth of space itself. This is why distant galaxies appear to recede faster the farther away they are. Beyond a certain point, expansion even carries galaxies away from us faster than the speed of light. Not because they are breaking relativity, but because the space between us and them is stretching so rapidly that light can never bridge the gap. All of this brings us back to the observable universe. The naive calculation of 13.8 billion light-years assumes space is static, but expansion multiplies that figure dramatically. As a result, the true radius of the observable universe is about 46.5 billion light-years, and its full diameter is about 93 billion light-years across. This revelation is staggering. The universe is more than 3 times larger than the age-based calculation would suggest, purely because space itself has been expanding relentlessly since the Big Bang. So, while the first estimate provides a neat starting point, the concept of an expanding universe blows open the doors of scale. It tells us that our observable bubble is not defined by a simple distance traveled by light, but by a complex interplay of time, space, and expansion. It reveals a universe that is dynamic, evolving, and far grander than our instincts first suggest. And as we peel back the next layer, we will see that expansion is not just about galaxies moving apart. It's about the very nature of space itself stretching, reshaping our understanding of reality at its most fundamental level. The concept of an expanding universe becomes even more mind-bending when we pause to consider what is actually expanding. It's tempting to imagine galaxies as projectiles launched outward in some grand explosion, racing through a pre-existing void of empty space. That image feels intuitive. After all, that's what happens when a firework bursts in the sky, or when shrapnel flies outward from an explosion. But the expansion of the universe is not like that at all. Galaxies are not racing through space like debris. Instead, space itself is stretching. This distinction is subtle but enormously important. When we say the universe is expanding, we don't mean that galaxies are zooming outward into some giant container of space. Rather, the container itself, the very fabric of spacetime, is growing. The galaxies are essentially standing still relative to their local regions of space, but as the fabric stretches, the distance between them increases. In other words, it's not motion through space that drives galaxies apart, it's the growth of space itself that carries them away from each other. The balloon analogy often helps, though it is imperfect. Imagine the surface of a balloon with tiny dots drawn on it. As the balloon inflates, the dots move farther apart, not because they're crawling along the balloon, but because the rubber surface is expanding. Likewise, galaxies in the universe are like those dots. They are not propelling themselves outward. Rather, the very stage on which they exist, the stage of spacetime, is expanding beneath them. There is no edge to the balloon's surface, no central point on the surface itself where the expansion begins. Expansion is uniform everywhere, and so it is with our universe. This realization has some surprising consequences. For one, it explains why very distant galaxies appear to recede faster than the speed of light. At first, this might sound like a violation of Einstein's relativity, which forbids objects from moving through space faster than light. But in this case, galaxies are not moving through space at all. They are being carried apart by the stretching of space itself. Relativity still holds, because no galaxy is locally breaking the speed limit. From their own perspective, galaxies are essentially at rest in their regions of space. It's the fabric between them that's growing. Another profound implication of space expanding is that it stretches not only galaxies apart, but also the very light that travels through it. This stretching of light is called cosmic redshift. As space expands, the wavelength of photons traveling across it is lengthened, shifting their color toward the red end of the spectrum. This effect was one of the key observations that led Hubble to realize the universe is expanding. The farther a galaxy is, the more its light has been stretched, and thus the redder it appears to us. This redshift is not due to galaxies racing away through space. It is direct evidence of space itself expanding. It's also important to note that the expansion of space does not happen on all scales. For example, your body isn't expanding, the Earth isn't swelling, and even our Milky Way galaxy is not stretching out. That's because gravity, and on smaller scales the electromagnetic forces, are strong enough to hold these systems together against the expansion of space. Expansion becomes dominant only on the largest scales, between galaxies and clusters of galaxies, where gravitational bonds cannot resist the overall stretching of the cosmic fabric. That's why the observable universe grows while our local corner of it remains bound and stable. One of the most counterintuitive aspects of space itself expanding is that there is no outside into which the universe is expanding. People often ask, what is the universe expanding into? The answer is that it's not expanding into anything. Space-time itself is what's growing, and the universe is all of space-time. Expansion does not require an external arena. Just as the balloon's surface expands without needing to move into a larger two-dimensional plane, our three-dimensional universe expands without requiring a higher dimensional container. This expansion also reshapes how we think about distance and time. When we say a galaxy is 10 billion light-years away, that doesn't mean its current location is simply 10 billion years of travel from us. Because space has stretched while the light was en route, the galaxy's present distance is much greater than the look-back time suggests. This distinction between light travel distance and proper distance, the galaxy's current separation from us, is critical. It's why the observable universe, though only 13.8 billion years old, spans a radius of about 46.5 billion light-years. Understanding that space itself expands also helps us grasp the dynamic nature of the cosmos. The observable universe is not a fixed bubble that we peer out of. It's a growing horizon, continuously changing as light from farther and farther regions finally reaches us. At the same time, there are regions of the universe whose expansion is so rapid that their light will never reach us, no matter how long we wait. These lie forever beyond our observable horizon. In fact, as dark energy accelerates cosmic expansion, more and more galaxies are slipping across that unreachable boundary, becoming forever invisible. In a sense, the expansion of space is both wondrous and tragic. It gives us a cosmos of staggering scale, filled with galaxies tens of billions of light years away. Yet it also places limits on our future view of the universe, cutting us off from much of what exists. Our observable horizon is vast, but it is also temporary. What we can see today is not what future civilizations will see. Billions of years from now, many of the galaxies visible in the night sky will have redshifted beyond detection, leaving only our local group of galaxies visible. The expansion of space defines not only what we can see now, but also what will remain visible in the cosmic future. So when we talk about the universe expanding, we are not describing galaxies racing away into pre-existing emptiness. We are describing the very stage of reality, the cosmic fabric itself, growing larger, carrying everything within it farther apart. This is why the observable universe is so much bigger than a simple age-based calculation suggests. And it is this stretching of space that leaves its mark on the light we observe, encoded in the form of cosmic redshift, the next key piece of evidence that shows us the universe is truly expanding. The idea that space itself is expanding is strange enough, but what makes it more than just a theoretical construct is that we can actually see the effects of this expansion written directly into the light that reaches us from distant galaxies. This effect is called cosmic redshift, and it serves as one of the most powerful pieces of evidence that the universe is stretching over time. Without it, the concept of expansion would be speculation. With it, expansion becomes undeniable. To understand redshift, we must first recall what light really is: a wave. Just like waves on the ocean, light has peaks and troughs, with the distance between them known as the wavelength. Shorter wavelengths correspond to bluer light, while longer wavelengths correspond to redder light. Now, here's where space expansion enters the story. As light travels across the cosmos, it doesn't move through a static backdrop. It journeys through a fabric of spacetime that is itself expanding. And as that fabric stretches, it drags the light waves along with it, lengthening their wavelengths. This stretching shifts light toward the red end of the spectrum, hence the term redshift. This is very different from the ordinary kind of redshift we encounter in everyday life, known as the Doppler effect. If a car speeds away from you, the sound waves it emits get stretched, and the pitch drops. Similarly, if a galaxy were physically moving away through space, its light would shift redward due to the Doppler effect. But in cosmology, the redshift we observe is not caused by galaxies racing through a fixed void. Instead, it arises because the space between us and those galaxies is expanding, and that expansion literally stretches the photons in transit. Edwin Hubble's breakthrough in 1929 came precisely from this observation. By studying the light from distant galaxies, Hubble discovered a systematic pattern. The farther a galaxy was, the greater its redshift. In other words, more distant galaxies looked redder than closer ones. This wasn't a coincidence. It was the signature of a uniform expansion of the universe. That discovery marked the birth of modern cosmology because it proved that the universe is not static but dynamic, unfolding on a cosmic scale. Cosmic redshift has since become the foundation of observational cosmology. Every major telescope, from Hubble to the James Webb Space Telescope, relies on measuring redshift to determine distances to galaxies and to reconstruct the history of cosmic expansion. When we detect a redshift in a galaxy's spectrum, we are not just learning how far away it is, we are literally measuring how much the universe has expanded since the light left that galaxy. For example, if the light from a galaxy has been stretched so that its wavelength is doubled, that tells us the universe has expanded by a factor of 2 during the light's journey. This effect becomes particularly striking when we look at the most distant galaxies. Some of them exhibit redshifts so extreme that their light has been stretched by factors of 7, 10, or even more. That means the universe has expanded 7-fold, 10-fold, or more in the time it took their light to reach us. The James Webb Space Telescope has already identified galaxies with redshifts corresponding to a time just a few 100 million years after the Big Bang. These galaxies are faint, ancient, and heavily redshifted, yet they carry within their photons a direct record of how dramatically the universe has stretched since its earliest days. Even more compelling is the fact that redshift is not limited to galaxies. The cosmic microwave background radiation CMB itself is the ultimate example of redshift in action. This radiation was originally emitted as searing hot light about 380,000 years after the Big Bang, when the universe was glowing at thousands of degrees Kelvin. But over the next 13.8 billion years, expansion stretched those photons so dramatically that their wavelengths shifted from visible light into the microwave part of the spectrum. That's why today, the CMB is a faint, cold glow at just 2.7 Kelvin above absolute zero. The very existence of the CMB in microwave form is irrefutable evidence that the fabric of the universe has been stretching since its beginning. Cosmic redshift also has another fascinating implication. It acts as a cosmic ruler. By measuring redshift, astronomers can map not only distances, but also the rate of expansion over time. This is how scientists discovered in the 1990s that the universe's expansion is accelerating, driven by some mysterious force we now call dark energy. Without redshift measurements, this revelation would have remained hidden. Yet, while cosmic redshift is the key to understanding expansion, it also places limits on what we can observe. The further away a galaxy is, the more redshifted its light becomes, and beyond a certain point, the light is stretched so much that it slips out of the visible or even infrared range, becoming undetectable. This creates a kind of observational horizon. There are galaxies beyond that horizon whose light is so redshifted by expansion that we will never see them. They are lost to us, hidden forever beyond the boundary of the observable universe. What makes cosmic redshift so powerful, though, is that it ties all of these ideas together. It is not just an abstract concept. It is something we can measure, record, and analyze. Every photon arriving at our telescopes carries a story, its wavelength stretched by the universe's history of expansion. Redshift transforms the night sky from a scattering of lights into a dynamic record of cosmic growth. It allows us to see, quite literally, the fingerprints of expansion imprinted on the cosmos. And so, cosmic redshift bridges the gap between theory and observation. It is the evidence that galaxies aren't just moving through space. Space itself is stretching. It is the reason we know the universe is expanding, the reason we know it had a beginning, and the reason we can measure its size today. And when we put this all together, the age of the universe, the finite speed of light, the concept of look-back time, and the stretching of light by cosmic expansion, we finally arrive at a staggering conclusion. The radius of the observable universe is not 13.8 billion light-years, but about 46.5 billion light-years. All of the pieces we've built up so far, the finite speed of light, the age of the universe, the concept of look-back time, the expansion of space, and the stretching of light through cosmic redshift, now converge into a single breathtaking realization. The observable universe is not limited to 13.8 billion light-years in radius, as the simple calculation might suggest. Instead, when we account for the expansion of space itself, the true radius of the observable universe is about 46.5 billion light-years. That means the diameter of our observable bubble is a staggering 93 billion light-years across. This number is almost incomprehensible. To put it another way, when we look at the most ancient light reaching us, the faint glow of the cosmic microwave background radiation, CMB, we are seeing photons that have been traveling for nearly 13.8 billion years. But because space has been stretching all that time, the regions that emitted that light are now much farther away than 13.8 billion light-years. In fact, they currently reside about 46.5 billion light-years from us. This is the subtle yet profound distinction between look-back time, the travel time of light, and proper distance, the current separation between us and the source. It's worth pausing here to make this clearer, because it can feel like a contradiction at first. If light has only had 13.8 billion years to travel, how can the source be 46.5 billion light-years away? The answer lies in the expanding fabric of space. Imagine placing an ant on a rubber band and slowly stretching the band while the ant walks toward you. Even if the ant walks for only a certain amount of time, the part of the band it started from may now be much farther away than the distance the ant actually walked, because the band itself has been stretching the whole time. Similarly, photons have been traveling toward us since the dawn of the universe, but the cosmic rubber band of space has expanded underneath them, so the points they came from are now vastly more distant. This radius of 46.5 billion light-years isn't just a mathematical curiosity. It has profound implications for how we think about our place in the cosmos. It means that the observable universe is far larger than our intuition might suggest. Large enough to contain at least 2 trillion galaxies, each with billions of stars. That's not the whole universe. That's just the part we can currently see. Beyond this observable bubble, the universe almost certainly continues, perhaps infinitely. But within our horizon, the scale alone is staggering. Every direction we look, out to 46.5 billion light-years, is filled with galaxies, nebulae, clusters, and vast structures stretching across unimaginable distances. This radius also serves as a kind of cosmic horizon line. It marks the boundary between what can, in principle, send us information and what can't. Anything farther away than 46.5 billion light-years lies beyond our causal contact. No light, no signal, no influence from those regions can ever have reached us since the Big Bang. And because the universe is not just expanding but accelerating due to dark energy, many of those regions will remain forever hidden, their light unable to bridge the widening gulf. The radius of 46.5 billion light-years is thus not just a measurement of size, it is a measurement of our knowledge limit. Interestingly, this value isn't static. Over time, the observable radius grows because light from farther and farther regions has had time to reach us. 1 billion years from now, the observable universe will be larger than it is today, encompassing regions currently beyond our horizon. However, due to the accelerating expansion driven by dark energy, there are also galaxies that will never become observable, because the space between us and them is expanding faster than light can cross. Our observable universe is a moving frontier, but it is also a shrinking window in some ways, cosmic structures slipping out of view as expansion pushes them irretrievably away. Another fascinating detail about the observable universe's radius is that it is symmetrical around us. No matter which direction we look, we see out to about 46.5 billion light-years. That might seem to imply we are at the center of the universe, but this is an illusion. The universe has no center. Every observer, no matter where they are, will see their own observable bubble with themselves at the center. An alien civilization 10 billion light-years away would have its own 40.5 billion light-year observable radius, overlapping with ours, but also stretching into regions we cannot see. The observable universe is thus not a privileged domain. It's simply our personal cosmic horizon. When cosmologists quote this figure of 46.5 billion light-years, they are doing more than answering a trivia question. They are telling us the extent of the cosmic stage accessible to us at this moment in time. It is the maximum scope of what we can scientifically study and understand through direct observation. Everything beyond that horizon lies outside our reach, not because it doesn't exist, but because its light hasn't had the chance to get here yet, and in some cases, never will. This number also forces us to confront the scale of human comprehension. 46 billion light-years is so vast that analogies begin to break down. Even the distance to the nearest star, Proxima Centauri, at 4.2 light-years, feels immense. The Milky Way galaxy spans about 100,000 light-years, which already strains our imagination. Yet, the observable universe is 465,000 times larger than the Milky Way's diameter. It contains galaxies so far away that their light began traveling toward us before the Earth even formed. The sheer immensity dwarfs everything we know on human scales, making the observable universe not just a number, but a source of existential wonder. So, when we say the radius of the observable universe is 46.5 billion light-years, we are stating the culmination of our best scientific understanding of cosmic expansion, light travel, and the geometry of space-time. It is the edge of our cosmic vision, a horizon carved by the interplay of light and time. But if the radius is 46.5 billion light-years, then the full diameter of the observable universe must be nearly 93 billion light-years across. an even more staggering scale, which we'll now turn to explore in greater detail. When we talk about the radius of the observable universe, we're describing how far we can see in one direction, about 46.5 billion light-years. But, of course, space extends in every direction, forming a vast spherical horizon around us. If you double that radius, you get the full diameter of the observable universe, roughly 93 billion light-years across. This number is one of the most staggering in all of science. It doesn't just dwarf human imagination, it challenges the very limits of what our minds can comprehend. To put this into perspective, let's first recall the scale of a single light-year. A light-year is the distance light travels in 1 year, nearly 9.46 trillion kilometers, about 5.88 trillion miles. That's already such a colossal distance that our own solar system barely makes a dent in it. The Voyager 1 spacecraft, humanity's most distant probe, has been traveling for almost 50 years and has only covered about 0.002 light-years. In other words, it hasn't even crossed the tiniest fraction of a single light-year, yet our observable universe spans 93 billion of them. The Milky Way galaxy, our home, is enormous by human standards, about 100,000 light-years across. It contains hundreds of billions of stars, countless planets, nebulae, and massive black holes. Yet the observable universe's diameter is about 930,000 times the width of the Milky Way. Imagine lining up nearly 1 million galaxies the size of the Milky Way end to end. That's the scale we're talking about. And remember, the observable universe contains not just 1 or 2 galaxies, but at least 2 trillion galaxies spread across this unimaginable expanse. Now consider galaxy clusters. The local group, which includes the Milky Way, Andromeda, and a few dozen smaller galaxies, stretches about 10 million light-years across. That feels vast, until you realize that the observable universe could fit about 9,300 local groups lined up in a row just to span its diameter. The largest structures we know, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall, extend over 1 billion light-years in length, making them almost inconceivably vast cosmic formations. Yet even these giants are minuscule compared to the full 93 billion light-year spread of the observable cosmos. It's important to recognize that when we speak of this 93 billion light-year diameter, we are not talking about the size of the entire universe, only the part we can see. Beyond our observable horizon, the universe may continue indefinitely. Some cosmological models suggest the whole universe is infinite, while others propose it may be finite but wrapped in a shape beyond our three-dimensional comprehension. The 93 billion light-year figure does not define the cosmos as a whole. It defines our cosmic bubble, the limit of what has been revealed to us by light since the Big Bang. This figure also underscores the distinction between the naive estimate and the reality of expansion. If we assumed the observable universe was limited to 13.8 billion light-years in radius, its diameter would be only about 27.6 billion light-years, still enormous, but far smaller than what we now know. Expansion has inflated that boundary by more than 3 times, giving us a full observable universe over 90 billion light-years across. The difference is not subtle. It's the difference between something merely massive and something so overwhelmingly vast that human language strains to describe it. And yet, even this 93 billion light-year sphere is temporary. It is not a fixed, permanent snapshot of the cosmos. Over time, the observable universe expands as light from ever more distant regions has time to reach us. Billions of years from now, intelligent beings may look out into a larger horizon than ours. But paradoxically, because the universe's expansion is accelerating, many galaxies that are currently visible will drift out of view forever, redshifting beyond detectability. This means the 93 billion light-year observable bubble is a fleeting, dynamic thing, a horizon unique to this particular cosmic moment. Another striking aspect of this number is its relativity. From our vantage point, the observable universe spans 93 billion light-years across, centered on Earth. But this is not because we are special or at the center of all things. Rather, every observer, anywhere in the universe, would measure their own observable universe to have the same diameter. If you were on a planet orbiting a star in a galaxy 20 billion light-years away, your observable bubble would still extend 46.5 billion light-years in every direction, overlapping with ours in some regions and reaching into areas we will never see. In this way, the observable universe is a personal horizon, not an absolute edge. This perspective also reveals a profound truth. What we see is only a fraction of the whole. If the observable universe is 93 billion light-years across, how big is the entire universe? We don't know. It could be hundreds of times larger, or it could be infinite. The observable diameter gives us a sense of scale, but it also reminds us of our limitations. We are peering out from a small point in an unfathomably vast cosmos, limited by time, light, and expansion. Beyond our horizon lies a reality we may never touch. So when we say the observable universe spans 93 billion light-years, we are not just stating a number. We are describing the grandest horizon of human knowledge, the largest map we can draw of reality itself. It is a figure that dwarfs galaxies, star clusters, and cosmic structures, a figure that redefines the word vast. And it serves as a reminder that the universe we see, the one we marvel at through telescopes, is only a bubble in a cosmos that may be infinitely greater. Now that we've revealed the true diameter of the observable universe, a natural question follows. Why is it so much larger than the age of the universe would suggest? To answer that, we must dive deeper into the consequences of expansion since the Big Bang and unravel why the universe's growth has made our observable bubble so enormous. When people first hear that the universe is 13.8 billion years old, they often jump to what feels like the obvious conclusion. The farthest we can see should be 13.8 billion light-years away. After all, if light travels at a fixed speed and has had 13.8 billion years to do so, that distance should define our cosmic horizon. But as we've uncovered, the observable universe is actually about 46.5 billion light-years in radius, or roughly 93 billion light-years across. That's more than 3 times larger than the naive estimate. The question is, why? How can the observable universe be so much bigger than its age seems to allow? The answer lies in the fact that the universe is not static. If the cosmos were a fixed, unchanging space, then yes, the farthest distance light could travel would be exactly its age in years, measured in light-years. But our universe has been expanding since the Big Bang. This expansion stretches not only the distances between galaxies, but also the light traveling through space. So while photons may have spent 13.8 billion years on their journey, the galaxies that emitted them have been carried far away by the stretching of space. Their present-day distance is far greater than the simple time times speed calculation suggests. To understand this more deeply, think again of the analogy of an ant crawling across a rubber band. Suppose the ant walks for 13.8 seconds, covering 1 unit of distance per second. If the band stayed the same size, the ant would end up 13.8 units away. But if the rubber band is being stretched continuously during those 13.8 seconds, the endpoint keeps receding even as the ant approaches. When the ant finally reaches its destination, the starting point has moved much farther than 13.8 units away. This is what happens to light in an expanding universe. The photons race toward us at the cosmic speed limit, but the stage they are crossing, the fabric of space, is stretching beneath them. By the time they arrive, their points of origin have been pulled tens of billions of light-years away. This is why the concept of look-back time is so important. When we say we are looking 13 billion years into the past, that refers to how long the light has been traveling. But the current distance to the source of that light is far greater because of expansion. A galaxy whose light we now see from 13 billion years ago is not 13 billion light-years away today. It may be 30, 40, or even more than 45 billion light-years away, depending on when the light was emitted and how much the universe has expanded in the meantime. The observable universe's radius of 46.5 billion light-years reflects this reality. It is the proper distance now to the edge of what we can see, not just the light travel distance. Another way to picture this is to imagine a race where the finish line itself is moving away from the runners. Light has been running toward us since the Big Bang, but the finish line, defined by the position of the source galaxy, has been pulled farther and farther back as space expanded. By the time the photons cross into our telescopes, the source galaxy is much farther away than the photon's travel distance suggests. This moving finish line is the essence of why the observable universe is so much bigger than its age would naively indicate. The mathematics behind this are built into what cosmologists call the scale factor, a measure of how much the universe has expanded over time. At the moment of the Big Bang, the scale factor was 0. Today, we define the scale factor as 1. When light was emitted billions of years ago, the scale factor was much smaller, meaning the universe was much more compact. As light traveled, the scale factor grew, stretching the distances between galaxies and elongating the wavelengths of photons. By tracking redshift, the stretching of light, we can calculate just how much the universe has expanded since those photons were emitted, and thereby determine the true current distance to their source. This also explains why we cannot simply equate the age of the universe with the size of the observable universe. The 13.8 billion year age tells us how long the universe has existed, but it does not directly tell us how far away the sources of the oldest light are now. Expansion ensures that those sources have receded to far greater distances, making our cosmic horizon vastly larger than a simple time times speed calculation would suggest. And here's a further twist. The expansion of the universe is not slowing down. In fact, it's accelerating due to the mysterious force we call dark energy. This acceleration means that galaxies beyond a certain distance will forever remain beyond our observational reach, because space between us and them is expanding faster than light can travel. This sets a kind of ultimate limit, a cosmic horizon beyond which we can never see, no matter how long we wait. The observable universe at 93 billion light-years across is not a static snapshot. It is a dynamic, evolving horizon shaped by both the age of the universe and the rate of expansion. So why is the observable universe so much bigger than its age suggests? Because space itself has grown. Light has faithfully carried information to us for 13.8 billion years, but the stage it crossed expanded as it traveled, inflating the distances to those regions to nearly 46.5 billion light-years away. The observable universe is therefore not a simple reflection of time. It is a reflection of time, light, and the expansion of space working together. This realization is one of the most awe-inspiring insights of modern cosmology. It means that the universe we see is far larger than our first instincts might allow, and that its growth is still ongoing. It also means that when we look out to the farthest reaches of space, we are not just seeing ancient galaxies, we are seeing galaxies that are now so far away that even if we could travel at the speed of light, we would never reach them. Expansion has locked them beyond our grasp, showing us both the immensity of the cosmos and the profound limits of our reach within it. Having grasped why the observable universe spans such an enormous distance, we now turn to one of the most significant markers of that limit: the cosmic microwave background, the faint afterglow of the Big Bang, which represents the true edge of what we can see. When we speak of the edge of the observable universe, we are not talking about a wall of stars or a sudden cutoff into nothingness. Instead, the farthest boundary of visibility is defined by the cosmic microwave background, CMB, a faint but all-encompassing glow that bathes the entire universe. This radiation is not only the oldest light we can see, it is also one of the most important discoveries in cosmology, providing us with a snapshot of the universe as it was just 380,000 years after the Big Bang. In essence, the CMB is the true edge of what we can observe, the farthest curtain of light marking the dawn of transparency in the cosmos. To understand why the CMB is the edge, we need to go back to the earliest moments of the universe. Immediately after the Big Bang, the cosmos was unimaginably hot and dense, a seething plasma of particles, photons, and energy. In this chaotic soup, light could not travel freely. Photons were constantly colliding with free electrons and protons, scattering endlessly, unable to move in straight lines. The universe, at that time, was opaque, like trying to see through the inside of the sun. For the first 380,000 years of cosmic history, no light could escape this blinding fog. But then, a dramatic change occurred. As the universe expanded, it cooled. At around 3,000 Kelvin, protons and electrons combined to form neutral hydrogen atoms, in a process known as recombination. With fewer free electrons to scatter them, photons were suddenly able to travel freely across space for the very first time. This moment transformed the universe from opaque to transparent, unleashing a flood of light that has been streaming across the cosmos ever since. That ancient light is what we now detect as the cosmic microwave background. Of course, the light from the CMB did not remain in its original form. At the time of recombination, it was brilliant and hot, glowing in the visible and infrared parts of the spectrum. But over the past 13.8 billion years, cosmic expansion has stretched its wavelengths enormously, shifting it down into the microwave portion of the spectrum. Today, the CMB is astonishingly cold, with a temperature of just 2.7 Kelvin above absolute zero. It is invisible to our eyes, but with the right instruments, like microwave receivers and radio telescopes, it appears as a faint but uniform glow across the entire sky. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was a watershed moment in science. At first, they thought the faint background signal they were detecting was interference or perhaps even bird droppings on their radio antenna. But after careful study, it became clear that they had stumbled upon the afterglow of the Big Bang itself. This discovery provided irrefutable evidence that the universe had a hot, dense origin, cementing the Big Bang theory as the leading explanation of cosmic beginnings. For this, Penzias and Wilson won the Nobel Prize in Physics, and the CMB became one of the most important pillars of modern cosmology. What makes the CMB so profound is not just that it exists, but what it reveals. The CMB is a snapshot of the infant universe. It shows us what the cosmos looked like when it was less than 400,000 years old, a baby picture of everything that exists. By studying its tiny variations, or anisotropies, scientists have learned about the density fluctuations that would eventually grow into galaxies and clusters. These ripples in the CMB are like the seeds of all cosmic structure, the fingerprints of the primordial universe etched into light. Space missions like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, measuring its temperature variations down to millionths of a degree. From this data, cosmologists have gleaned astonishing insights: the age of the universe, the proportions of dark matter and dark energy, the geometry of space-time, and even hints about the inflationary period that may have occurred in the earliest fractions of a second after the Big Bang. The CMB is not just the edge of what we can see. It is the most informative window we have into the fundamental nature of reality. It's important to note that the CMB is not the literal end of the universe. Beyond it, there is more universe, but it is forever hidden from us in terms of electromagnetic light, because photons from earlier times simply could not travel freely. The CMB forms a cosmic horizon, the limit of how far back in time we can see with light. It is like standing at the shore of an infinite ocean, gazing out at the foggy horizon. We know there is more beyond, but it is concealed, unreachable by direct observation. And yet, even though it marks the edge of what we can see, the CMB connects us to the entire cosmos in a remarkable way. Every direction we look, no matter where we aim our detectors, we see the same faint glow, because it comes from the time when the whole universe was young and uniform. This universality is humbling. The CMB is not the light of stars or galaxies, it is the light of creation itself, filling every inch of the sky equally. So, when we talk about the observable universe being 46.5 billion light-years in radius, the true edge is defined by this afterglow. It is not the edge of matter or of existence, but the edge of light, the point beyond which photons cannot carry us. Beyond that boundary, the universe continues, but it is invisible to our eyes and telescopes. The CMB is therefore not just the limit of observation, it is a symbolic reminder that the universe, vast as it appears, holds mysteries forever hidden beyond the horizon. From this vantage point, we now see the observable universe as a bubble, its surface traced by the CMB. But beyond that bubble, space doesn't simply stop. There is more universe out there, stretching into the unseen and perhaps the infinite. And this leads us to the next great question: what lies beyond the observable limit? When we talk about the observable universe, we must always remember that this word, observable, is a qualifier, not a description of the cosmos in its entirety. The 93 billion light-year wide bubble we describe as the observable universe is not the universe itself. It is simply the part of the universe that has had enough time to send us light since the Big Bang. Beyond that boundary, the cosmic horizon marked by the cosmic microwave background, there is almost certainly more universe. In fact, the overwhelming consensus among cosmologists is that the universe extends far beyond what we can see, perhaps unimaginably farther, and perhaps without end. Why are we so confident that more exists beyond the horizon? For one, the laws of physics do not suggest that the universe suddenly ends at 46.5 billion light-years. Nothing in general relativity, or in our observations, hints at a hard edge where space or matter stops. Instead, what we encounter is simply the limit of visibility. The universe continues, but the light from those farther regions has not had enough time to reach us in the 13.8 billion years since the Big Bang. In other words, the observable universe is a horizon, like the horizon you see standing on the Earth. Just as you know the planet continues beyond what your eyes can perceive, the cosmos almost certainly extends beyond our observational reach. There is also a strong argument from the cosmological principle, the assumption that on large enough scales, the universe is homogeneous and isotropic, that is, roughly the same everywhere. When we look in different directions, the universe appears uniform. The distribution of galaxies, the temperature of the CMB, and the overall structure of space are consistent to astonishing precision. If the observable portion of the universe looks this way in every direction, the most reasonable conclusion is that the universe continues in a similar fashion beyond our horizon. The patch we see is not special. It is part of a far larger whole. What's more, theoretical models like cosmic inflation strongly support the idea of a universe vastly larger than the observable region. Inflation proposes that in the first fractions of a second after the Big Bang, the universe underwent an extraordinarily rapid expansion, growing exponentially faster than the speed of light, not in violation of relativity, because it was space itself expanding. This inflation would have stretched tiny quantum fluctuations into the seeds of galaxies and clusters we see today, while also ensuring that the universe looks flat and uniform on large scales. But inflation doesn't stop neatly at the edges of our observable bubble. It suggests that space may extend far beyond what we can ever see, perhaps by factors so large they defy human language. This raises a staggering possibility. The entire universe might be hundreds, thousands, or even trillions of times larger than the observable universe. Some models even suggest it could be infinite. If that's the case, then our 93 billion light-year wide bubble is just a speck, a tiny, local patch in an endless expanse of spacetime. The galaxies we see, the vast structures that already dwarf human imagination, may be nothing more than a minuscule sample of the cosmic whole. But here's the humbling part. Because of the finite age of the universe and the ongoing acceleration of cosmic expansion, much of this greater universe is forever hidden from us. There are galaxies out there whose light will never reach us, no matter how much time passes, because space between us and them is expanding faster than light can bridge. This creates a kind of event horizon, a limit not only on what we can see now, but on what we will ever be able to see. The universe is filled with wonders that will remain permanently beyond our reach, hidden behind the veil of expansion. Still, this does not render the greater universe irrelevant. In fact, acknowledging that there is more beyond what we can see is crucial to understanding our place in the cosmos. Our observable bubble is like a window into an endless ocean. We can measure the waves within our sight, map their patterns, and learn the rules by which they behave. But the ocean doesn't stop at the edge of the window. It continues indefinitely, whether we can see it or not. The observable universe is the part revealed to us, but it is not the full story. This realization also reshapes how we think about uniqueness. If the universe truly extends far beyond our horizon, then the galaxies, stars, and planets we see are just a sampling of an unfathomable abundance. There may be structures so vast or so exotic beyond our view that we cannot even imagine them. If the universe is infinite, then every possible arrangement of matter, however improbable, could exist somewhere out there, including galaxies eerily similar to our own, or even regions with properties so alien that they defy our physics. Of course, we must be careful here. Beyond the observable horizon, we cannot observe directly, which means we cannot know for certain. We can only infer based on the physics we do understand and the uniformity we observe within our bubble. It is possible, though not supported by current evidence, that the universe could be finite and have a shape that eventually wraps around on itself, like the surface of a sphere. But even in that case, it would still extend far beyond the 93 billion light-year diameter we can currently access. So, what lies beyond the observable limit? Almost certainly, more universe, more galaxies, more stars, more cosmic structures stretching farther than light can ever carry their existence to us. Perhaps even an infinite expanse. The observable universe is thus not the totality of existence, it is simply the limit of our vision. And this distinction is crucial because it leads us directly to one of the deepest and most debated questions in cosmology. Is the universe truly infinite, or is it finite but vastly larger than the part we can see? The realization that the observable universe is merely a bubble within something larger naturally leads us to one of the most profound questions in all of cosmology. Is the universe itself infinite or finite? This is not just an abstract debate. It is a question that cuts to the very heart of reality. If the universe is infinite, then the cosmic expanse stretches without end, containing an unbounded number of galaxies, stars, planets, and perhaps even regions with laws of physics different from our own. If it is finite, then the universe has a definite size, though one so vast that it dwarfs everything we can see. Both possibilities are staggering in their implications, and both challenge human imagination. Let's start with the infinite possibility. The idea of an infinite universe means that space extends forever, with no boundary, no edge, and no stopping point. In such a universe, the observable cosmos, the 93 billion light-year-wide sphere we inhabit, is just a vanishingly small fraction of the whole. Beyond our horizon, the same kinds of galaxies and structures continue endlessly, forever hidden from us by the limits of light and expansion. If true, this would mean there is no ultimate scale to the universe, no largest structure, no final frontier, just an eternal sea of space-time. But infinity raises puzzles of its own. If the universe is infinite, then it contains an infinite number of stars and galaxies. In fact, it would contain an infinite number of every possible configuration of matter. That would mean, in theory, there are infinite versions of Earth, infinite versions of you, and infinite variations of every possible cosmic history. This idea, often called the cosmic doppelganger argument, flows naturally from infinity. Somewhere, infinitely far away, there could be a galaxy identical to the Milky Way, with a planet identical to Earth, with a person identical to you reading these exact words. Infinity erases uniqueness, replacing it with endless repetition of all possibilities. Now, let's turn to the finite option. A finite universe does not necessarily mean small. It could still be unimaginably huge, hundreds or thousands of times larger than the observable universe. If the universe is finite, it might even be curved in such a way that space wraps around on itself. Imagine walking around the surface of a sphere. You never encounter an edge, but the surface is finite. Similarly, space could be shaped like a higher dimensional version of such a sphere, a hypersphere, looping back on itself. In such a universe, if you traveled far enough in a straight line, you might eventually return to your starting point, not because you turned, but because space itself is curved. This raises an interesting point. The observable universe cannot directly tell us whether the universe is finite or infinite. Our horizon is limited, and beyond it, we can only infer. The geometry of space, however, gives us clues. Measurements of the cosmic microwave background, CMB, particularly by satellites like W, M, AP, and Planck, suggest that the universe is spatially flat to a very high degree of precision. Flatness implies that, on the largest scales we can measure, space does not curve back on itself. A truly flat universe could be infinite, though it is also possible for a flat universe to be finite if it wraps around in a toroidal, donut-like shape. But the fact that it appears flat on scales of hundreds of billions of light years strongly supports the possibility that it is infinite. Cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, also provides insight. Inflation predicts that the universe should be vastly larger than the observable patch we inhabit, perhaps exponentially larger. Many versions of inflation even suggest that the universe must be infinite, or at least so large that it is practically indistinguishable from infinity. If inflation occurred as most models describe, then the observable universe is just a tiny bubble in a far greater expanse. Still, we must be cautious. While the evidence leans toward flatness and thus the possibility of infinity, we cannot observe beyond our horizon. It may always remain a matter of inference rather than direct observation. For all we know, the universe could be finite, but so immense that the difference makes no practical impact. Whether finite or infinite, the scale is so enormous that the observable universe is only a sliver. The philosophical implications are immense. If the universe is infinite, then the concept of uniqueness dissolves. Every configuration of matter, no matter how improbable, must exist somewhere. If it is finite, then the universe has a definite size, and we live in a cosmos with a measurable boundary, though one far beyond what we will ever see. Both scenarios are humbling. In one, we are surrounded by infinite repetition. In the other, we are inhabitants of a vast but bounded structure whose edges lie forever beyond our perception. What's remarkable is that even though we may never know for sure, our observations allow us to narrow the possibilities. The flatness of the CMB, the success of inflationary theory, and the consistency of large-scale structures all point toward a universe far larger than what we can see, and possibly infinite. The observable universe is huge, but it is not the whole. It is a window, perhaps onto infinity, perhaps onto an immense but finite expanse. And so, when we ask the question, infinite or finite, we are really probing the limits of human knowledge itself. For now, the evidence leans toward infinity, but humility reminds us that our cosmic horizon is just one perspective. Beyond it may lie truths stranger and grander than we can yet conceive. And this brings us to the role of current evidence, the scientific measurements and data that give us the best clues about the true nature of the cosmos. The question of whether the universe is infinite or finite is not one we can answer by looking beyond our horizon, because by definition, we cannot see beyond it. But what we can do is examine the universe within our observable bubble and use the clues it leaves us to infer its larger structure. This is where current evidence from modern cosmology comes into play, and in particular, the data gathered from missions like WMAP, Wilkinson Microwave Anisotropy Probe, and Planck. These missions have provided us with extraordinarily detailed measurements of the cosmic microwave background, the faint afterglow of the Big Bang, and in doing so, they've reshaped our understanding of the universe's size and shape. When cosmologists talk about the shape of the universe, they are referring to its geometry. Space can be flat, positively curved, or negatively curved. A positively curved universe is like the surface of a sphere, finite but unbounded. A negatively curved universe is like a saddle, infinite but with a distinct curvature. A flat universe is, well, flat, extending indefinitely in all directions without curvature. Which of these geometries the universe has depends on the overall density of matter and energy compared to a critical threshold predicted by general relativity. If the universe has more than this critical density, space curves positively. Less than the critical density, and space curves negatively. Equal to the critical density, and space is flat. So, what do the data tell us? Both WMAP and Planck measured the tiny temperature fluctuations in the CMB with exquisite precision, mapping them across the sky. These fluctuations are like imprints of sound waves rippling through the early plasma of the universe. By studying the angular scale of these ripples, cosmologists can determine the curvature of space itself. The results have been stunning. The data show that the universe is flat to within a margin of error of just 0.4%. In other words, on scales of hundreds of billions of light years, the universe appears to be flat, not curved. This finding is enormously important. A flat universe strongly suggests that the cosmos is either infinite or so large that its curvature is undetectable within the observable horizon. If the universe were small and finite, we would expect to see evidence of curvature in the CMB, but none appears. Planck's data in particular, released in 2013 and refined in subsequent years, confirmed this flatness with remarkable precision. From a scientific standpoint, the simplest explanation is that the universe extends far beyond our observable bubble, likely unimaginably farther. WMAP and Planck also provided critical evidence for the composition of the universe, which in turn influences its geometry and fate. They revealed that ordinary matter, the atoms that make up stars, planets, and people, accounts for only about 4.9% of the total cosmic content. Dark matter makes up about 26.8%, while the mysterious dark energy, which drives the accelerating expansion of the universe, comprises roughly 68.3%. These numbers matter because they add up to exactly the critical density required for flatness. The balance is extraordinary. All the matter and energy in the cosmos, including the invisible dark components, perfectly align to create a flat universe. This result is not only astonishing, but also consistent with the predictions of cosmic inflation, which smoothed and flattened the universe in its earliest moments. Beyond geometry, the CMB data also offer clues about the size of the universe. While we cannot measure the full extent directly, we can place limits. If the universe is finite and positively curved, it must be at least several hundred times larger than the observable universe. Otherwise, its curvature would have shown up in CMB patterns. In other words, even in the most conservative scenario, the universe is staggeringly larger than what we can see. And if the flatness measured by Planck holds true to all scales, then the universe may be truly infinite. Other lines of evidence reinforce this picture. Observations of large-scale structure, the distribution of galaxies and galaxy clusters across space, show the same uniformity and flatness as the CMB. Studies of baryon acoustic oscillations, the frozen imprints of early sound waves in the distribution of matter, also confirm the same geometry. Together, these datasets converge on a single, consistent story. The universe is flat, and it is vastly larger than the observable horizon. Yet, we should note that there are still open questions. Some recent studies have hinted at tiny anomalies in the CMB, subtle asymmetries, unexplained cold spots, that may or may not point to something beyond our current models. These could be statistical flukes, or they could be the first hints of new physics. If they are real, they might eventually refine our understanding of the universe's shape and size. For now, though, the overwhelming weight of evidence supports flatness and vastness. What all this means is that the observable universe, the 93 billion light-year-wide sphere we inhabit, is not the whole story. It is just a sample, a tiny bubble in a cosmos that is either infinite or so colossal that the difference hardly matters. WMAP, Planck, and other missions have not just confirmed the size of our observable bubble. They have opened our eyes to the likelihood that the universe stretches far, far beyond it. And this distinction leads us to another vital clarification: the difference between the observable universe and the whole universe. We've measured the former with astonishing precision, but the latter remains shrouded in mystery, perhaps forever beyond our reach. Up to this point, we've been speaking of the observable universe, the 93 billion light-year bubble of space we can see. But it's crucial to pause here and make a clear distinction. The observable universe is not the same thing as the whole universe. The difference between these two concepts is enormous, and confusing the two can lead to major misunderstandings about our cosmic place. The observable universe is defined by the limits of light travel. Because the universe has a finite age, about 13.8 billion years, and because light moves at a finite speed, there's only so much of the cosmos that has had time to send signals to us. That horizon defines the observable bubble, centered on us. Within it, we can measure galaxies, map structures, and detect the cosmic microwave background. Beyond it, we cannot see directly, because light from those regions has not yet had time to arrive. The whole universe, however, is something far grander. It includes not only what we can see, but also everything beyond the cosmic horizon. If the universe is infinite, then the whole universe is boundless, extending endlessly in all directions. If the universe is finite but vast, then the whole still dwarfs our observable slice, encompassing regions that lie forever outside our reach. Either way, the whole universe is far larger than the observable universe. Our bubble is just a window, not the entire structure. Think of it like this. Imagine standing in the middle of a dense fog on a plane. You can only see a certain distance around you. That circle of visibility is your observable universe. But you know the plane continues far beyond the foggy horizon, even if you can't see it. Similarly, our observable horizon doesn't mean the universe ends there. It simply marks the limit of what has been revealed to us so far. This distinction matters for another reason. It avoids the misconception that Earth, or our galaxy, sits at some kind of privileged center of existence. When we say the observable universe is centered on us, that's not because we are cosmically special. It's because every observer, no matter where they are, has their own observable bubble. A galaxy 10 billion light-years away from us would also have its own horizon extending 46.5 billion light-years in all directions. Their observable universe would overlap with ours in some regions, but extend into areas we can never see. This relativity of observation is built into the fabric of space-time itself. Understanding the difference between the observable and the whole universe also helps us remain humble in our claims. We can say with confidence that the observable universe has a radius of 46.5 billion light-years and contains at least 2 trillion galaxies. But when it comes to the whole universe, our knowledge stops at inference. Based on the evidence from the cosmic microwave background and large-scale structures, we strongly suspect the universe extends much farther, perhaps infinitely. Yet, we must admit, we cannot observe it directly, and perhaps never will. This leads to one of the most profound philosophical points in cosmology. Science thrives on observation, on testing theories against what we can measure. The observable universe fits beautifully within that framework. We can map it, quantify it, and compare predictions with reality. The whole universe, however, lies partly beyond observation, which means it may always retain an element of mystery. It reminds us that there are limits to what humans can know, boundaries to our cosmic vision. Still, by distinguishing between observable and whole, we gain clarity. The observable universe is our laboratory, the part of the cosmos we can study and understand. The whole universe is the vast ocean beyond, inferred from theory and evidence but not directly seen. When cosmologists talk about size, scale, and structure, they are usually careful to emphasize which of these two they are discussing. Mixing them up is like confusing the shoreline you can see with the entire ocean that stretches beyond the horizon. And yet, even within this observable bubble, there is a humbling truth. Every observer in every galaxy experiences their own personal cosmic horizon. This brings us to the next astonishing realization. Every observer has their own bubble of the observable universe, each centered on themselves, each just as valid as ours. One of the most humbling and beautiful truths about cosmology is that the observable universe is not unique to us. While we often speak of our observable universe, centered here on Earth, stretching 46.5 billion light-years in every direction, the same principle applies to every other location in the cosmos. Any observer, no matter where they are, would see their own observable bubble surrounding them. Each bubble has the same radius, each marks the limit of visibility set by light and time, and each is centered on the observer's position. This is not because Earth is special, or because humanity occupies a privileged place in the cosmos, but because the laws of physics apply equally everywhere. Imagine an alien civilization living in a galaxy 10 billion light-years away. From their perspective, their observable universe would also span 46.5 billion light-years in every direction, centered on their world. Their horizon would overlap with ours in some regions, showing many of the same galaxies, but it would also stretch into regions we cannot see. Their night sky, though governed by the same cosmic rules, would look different, filled with galaxies and structures beyond our horizon but within theirs. To them, their universe would feel complete, just as ours does to us. This idea, that every observer has their own bubble, is a direct consequence of the cosmological principle, the notion that the universe is homogeneous, the same in every large-scale region, and isotropic, the same in every direction. When viewed on cosmic scales, it means there is no center of the universe, no privileged vantage point. Instead, every galaxy can consider itself the center of its own observable sphere. Earth just happens to be the center of ours because it's where we are. If we were on a planet orbiting a star in Andromeda, or in a galaxy billions of light-years away, we would still see a bubble stretching out equally in all directions, bounded by the same physics. This realization dissolves an old human bias, the idea that we occupy a special place in the cosmos. For much of history, humanity assumed we were at the center, first of the Earth, then the solar system, then the galaxy. Modern cosmology shows us instead that we live in a universe where every vantage point is equally central within its own observable bubble. The center is not a privileged cosmic location. It is a relative perspective created by the finite age of the universe and the speed of light. What's even more astonishing is how these bubbles overlap and connect. Our observable universe contains galaxies that are also within other observers' bubbles. That alien civilization 10 billion light-years away might see our Milky Way, just as we might one day detect faint signals from their galaxy. But their horizon extends into regions we will never see, and our horizon extends into regions they cannot see. The whole universe is thus a vast mosaic of overlapping observable bubbles, each unique to the observer, each just a fraction of the total cosmos. This perspective also underscores the relativity of knowledge. When we say the observable universe is 93 billion light-years across, what we mean is our observable universe. It is the bubble defined by our position in space and our moment in cosmic time. Another civilization in a different galaxy would quote the same number for their bubble, but they would be speaking of a different slice of the universe. The observable universe is not an absolute thing. It is a personal horizon, carved by light, time, and perspective. There's something profoundly humbling about this. It means that even as we map galaxies billions of light-years away, we are still looking from a very local viewpoint. We are seeing only what our position allows, only what light has had time to bring us. To truly know the whole universe, we would need to gather the perspectives of countless observers scattered across the cosmos. But, of course, that is impossible, because the distances between horizons are too great and communication is forever constrained by the speed of light. Each bubble is a self-contained window, unique to its observer. And yet, this doesn't diminish our discoveries. On the contrary, it deepens them. By understanding that every observer has their own bubble, we realize that our observations are not special or isolated. They are part of a universal pattern. We are not at the center of the cosmos, but we are at the center of our own cosmic horizon, just as every galaxy is. The universe, then, is a grand tapestry of perspectives, each equally valid, each equally profound. Recognizing this also prepares us to think about scale. If every observer's horizon is 93 billion light-years across, how do we make sense of such vastness? How do we relate these cosmic numbers to the structures we are more familiar with? Stars, galaxies, and even our own Milky Way. To appreciate the sheer immensity of the observable bubble, we must turn to scale comparisons, bridging the humanly comprehensible with the cosmically incomprehensible. The figure 93 billion light-years across is so vast that at first glance, it feels more like an abstract mathematical curiosity than something we can truly imagine. Our human brains evolved to understand distances we could walk, run, or maybe sail across, kilometers, miles, perhaps thousands at most. Once we move beyond planetary scales, the numbers become so enormous that they strain comprehension. To appreciate just how immense the observable universe really is, it helps to compare it step by step to the structures we know more intimately: our solar system, our galaxy, and the galaxies beyond. Let's start close to home. The Earth orbits the Sun at a distance of about 150 million kilometers, roughly 8 light minutes away. That's right, light, the fastest thing in the cosmos, takes over 8 minutes just to cross from the Sun to Earth. The outer edge of our solar system, where the Oort cloud of icy comets may extend, is perhaps a light year or two away. Even if we were to count that generous boundary, our entire solar system would span less than a few light years across. To our human perspective, that's enormous. But against the scale of the universe, it is barely a microscopic dot. Now, expand to our galactic home, the Milky Way. Our galaxy is a sprawling disk of stars, gas, and dark matter about 100,000 light-years across. Containing an estimated 200 to 400 billion stars, it is a vast cosmic city, with spiral arms sweeping gracefully through space. Traveling at the speed of light, it would take 100,000 years to cross from one side of the Milky Way to the other. Even within this enormous span, our solar system is just one unremarkable neighborhood, orbiting a star halfway out from the galactic center. Beyond the Milky Way lies our local group, a cluster of more than 50 galaxies bound together by gravity, including the Andromeda Galaxy, about 2.5 million, light-years away, and many smaller companions. The local group itself spans about 10 million light-years across. If we zoom out further, we encounter the Virgo supercluster, which encompasses thousands of galaxies over a region roughly 110 million light-years in diameter. Already these distances dwarf the Milky Way, and yet they are still infinitesimal compared to the observable universe. Here's where the scale becomes staggering. The observable universe is 93 billion light-years across. That means it is nearly 1,000,000 times larger than the Milky Way. To picture this, imagine shrinking the Milky Way down to the size of a grain of sand. If you placed that grain in your hand, the observable universe would still span larger than the Earth itself compared to your tiny grain. Or consider this. If you could line up Milky Way's edge to edge like cosmic pearls, you would need nearly 1,000,000 of them to stretch across the diameter of the observable universe. Even galaxy superclusters, the largest structures we know of within our observable bubble, are dwarfed by this scale. The Hercules Corona Borealis Great Wall, the largest known structure in the universe, is about 10 billion light-years long. That's unimaginably vast compared to galaxies, but it is still only about 1/9 the diameter of the observable universe. The cosmos contains structures so immense they strain our imagination, and yet, even these are small on the scale of the whole observable bubble. To put it another way, the observable universe's diameter of 93 billion light-years is not just big, it is beyond our ability to intuitively grasp. If you traveled at the speed of light, the maximum speed allowed by the laws of physics, it would take you 93 billion years to go from one edge of the observable universe to the other, over 6 times longer than the universe itself has existed. That paradox is resolved, of course, by cosmic expansion, but it highlights the sheer enormity of the numbers involved. And then there's the question of galaxies within this bubble. Current estimates suggest that the observable universe contains about 2 trillion galaxies. Each galaxy may contain hundreds of billions of stars, and many of those stars may host planets. The Milky Way, impressive as it is, becomes just one grain of sand among trillions scattered across the cosmic shore. The observable universe is not just large in terms of physical distance, it is staggeringly rich in structure and content. So, how do we compare 93 billion light-years to our everyday experience? The truth is, we can't. Not directly. Any attempt at an analogy quickly collapses under the weight of such enormity. We can shrink galaxies to sand grains, stack Milky Ways across space, or measure the journey in lifetimes, but the result is always the same. The observable universe is so vast that human intuition falters. Our minds simply aren't built to hold numbers this big, and yet, this very struggle is part of the beauty of cosmology. It reminds us that the universe is not designed to be comfortable or intuitive to human senses. Instead, it challenges us to stretch our imagination, to build mathematical models, and to rely on careful measurements to understand what lies beyond our natural grasp. The observable universe's 93 billion light-year scale is not something we feel. It is something we learn through the patient accumulation of data and the ingenuity of science. This brings us naturally to the next point, our human comprehension limits. Why is it that numbers like 93 billion light-years overwhelm us? Why is it that our brains resist such scales? And how do scientists make sense of them when intuition fails? Standing in awe before the figure of 93 billion light-years, one quickly runs into the limits of human comprehension. Our brains evolved to navigate landscapes, avoid predators, find food, and cooperate with others. We are finely tuned to deal with distances measured in meters, kilometers, or at most a few hundred kilometers. The leap from a football field to the span of a country, or even to the circumference of the Earth, is still something we can picture. But when we step into the realm of light years, galaxies, and cosmic scales, our intuition simply breaks down. Consider the light year. It is defined as the distance light travels in a year, about 9.46 trillion kilometers, 5.88 trillion miles. Already, this is such a vast distance that it defies mental imagery. A single light year is more than 60,000 times the distance from Earth to the Sun. And yet, a light year is the basic unit of distance in astronomy, a stepping stone to describe much larger spans. When we say the Andromeda Galaxy is 2.5 million light-years away, that number is essentially beyond our natural comprehension. When we scale up to 93 billion light-years across for the observable universe, it becomes purely abstract. Psychologically, this makes sense. The human brain did not evolve to conceive of billions of anything, let alone billions of years or billions of light-years. We understand hours, days, maybe lifetimes. We can picture walking to a nearby town or driving across a country, but we cannot naturally imagine a journey that would take longer than the existence of humanity itself. Cosmic timescales and distances dwarf our biological sense of proportion. This is why cosmologists rely on mathematics, models, and analogies. Mathematics gives us a framework to calculate and compare distances that are otherwise incomprehensible. A scientist can say, the universe is 93 billion light-years wide, not because they can imagine it in a literal sense, but because the equations of relativity, the measurements of redshift, and the mapping of the cosmic microwave background all point to that number. Mathematics liberates us from the prison of human intuition and gives us a language to describe the indescribable. Analogies, on the other hand, help bridge the gap between the cosmic and the everyday. We shrink the Milky Way down to the size of a coin, or describe the observable universe as a grain of sand on a vast cosmic beach. These metaphors don't fully capture the reality, but they give us footholds. They allow us to approach an understanding that our minds would otherwise reject outright. It is why teachers, astronomers, and science communicators lean so heavily on comparisons to familiar scales. We need anchors in the sea of the incomprehensible. Models and simulations provide another tool. By creating visualizations of galaxy clusters, cosmic webs, or light cones, scientists can represent the structure of the universe in a way that the human mind can at least partially grasp. Seeing the universe as a web of filaments, with galaxies strung like beads on strands of dark matter, gives us a sense of organization, even if the sheer size still escapes us. These models do not shrink the universe down to something comprehensible in the human sense, but they transform raw numbers into patterns we can analyze and relate to. But perhaps the most important recognition is humility. We must admit that we cannot feel what 93 billion light-years means. Our sense of scale collapses long before we get there. We are trying to imagine a reality where distances are measured in trillions of kilometers, where timescales span billions of years, and where galaxies are as common as grains of sand. To us, these numbers are surreal abstractions. To the universe, they are everyday facts. This mismatch can be deeply humbling. It reminds us that the universe is not shaped by human perception. The cosmos is not designed to be intuitive. Our brains, powerful though they are, evolved for survival, not for cosmology. And yet, through the tools of science, we have stretched our understanding far beyond our evolutionary constraints. We cannot imagine 93 billion light-years, but we can calculate it, describe it, and work with it. That is one of humanity's greatest achievements, the ability to build intellectual tools that extend beyond our natural senses. In some ways, our struggle to comprehend cosmic scale is part of the beauty of astronomy. It reminds us that there is always more to learn, always deeper mysteries waiting just beyond our reach. The size of the observable universe is not just a scientific fact, it is a mirror, showing us the limits of human imagination and the power of human reason. It tells us that our place in the cosmos is tiny, but our capacity to explore it, at least intellectually, is vast. And this brings us to an important question. Why does it matter? Why should we care about the size of the observable universe at all, if it is so far beyond our comprehension? The answer lies not just in science, but in perspective. Understanding the cosmos gives us a deeper sense of our origins, our place, and our destiny. The sheer size of the observable universe, 93 billion light-years across, is not just a piece of trivia to awe us at star parties or fuel curiosity in documentaries. It is a cornerstone of cosmology, a figure that connects us to the deepest questions about reality, origins, and destiny. Understanding why it matters means moving beyond the shock of big numbers and appreciating how the scale of the observable universe reveals the very nature of the cosmos and our place within it. First, the size of the observable universe is direct evidence for the Big Bang. The fact that we can detect light from 46.5 billion light-years away, and that this light has been stretched and redshifted by cosmic expansion, shows us that the universe had a beginning and has been growing ever since. The discovery of the cosmic microwave background and the realization that the galaxies we see at different distances represent different stages of cosmic history weave together into a consistent story. The universe was born hot and dense, expanded rapidly, and continues to expand today. Without knowing the size of the observable universe, We could not test this model against reality with such precision. Second, the vastness of the observable universe is a laboratory of extremes. Within our horizon, we see galaxies forming, colliding, and evolving. We see the remnants of the early universe in the CMB. We observe black holes, quasars, and cosmic webs of dark matter stretching across hundreds of millions of light years. The larger the observable universe, the more of these phenomena we can study. Each distant galaxy is a data point. Each photon that has traveled for billions of years is a messenger from the past. The scale of the observable universe ensures that we have a rich archive of cosmic history, a tapestry large enough to test fundamental theories about matter, energy, and space-time itself. Third, it places humanity in cosmic perspective. When we realize that our observable universe contains 2 trillion galaxies, each with hundreds of billions of stars, we begin to grasp just how small and fragile our own world is. Earth, for all its beauty and complexity, is one planet orbiting one star in one galaxy among trillions. Knowing the size of the observable universe is a humbling reminder that we are not at the center, nor are we unique in the grand structure of reality. It shifts our thinking from anthropocentrism to cosmocentrism, a worldview shaped by the universe itself. And yet, this humility is paired with a kind of wonder. Though we are small, our minds have stretched to measure and understand the vastness around us. The fact that we can map 93 billion light-years of space from a tiny rock orbiting a star is a triumph of human curiosity and intellect. It connects us not just to science, but to a kind of cosmic awe, a sense that we are participants in something much larger than ourselves. The size of the observable universe also matters because it defines the limits of our knowledge. Beyond 46.5 billion light-years we cannot see. There may be more galaxies, more structures, perhaps even phenomena we cannot imagine. But they remain forever hidden, behind a horizon we cannot cross. In this way, the observable universe is not just a measure of what exists, it is a measure of what we can know. It teaches us humility in science. Even with the most powerful telescopes, even with the best theories, there are boundaries to observation. At the same time, understanding the size of the observable universe informs our future. The accelerating expansion driven by dark energy means that over billions of years, more and more galaxies will slip beyond our horizon. Future civilizations may look out into the night sky and see only the faint glow of our local group, with the rest of the cosmos invisible. For us, living at this particular moment, the observable universe is vast and filled with galaxies. Knowing its size connects us to the fleeting nature of this cosmic window of opportunity. Finally, the sheer immensity of the observable universe forces us to confront questions of meaning. If the universe is this large, what does it say about life, intelligence, and our role in the cosmos? Are we alone in a bubble filled with trillions of galaxies, or is life scattered everywhere, hidden in distant corners we cannot yet reach? Knowing the scale deepens these mysteries, turning them from parochial concerns into cosmic ones. It reminds us that our search for meaning is not just about Earth, it is about the entire universe we inhabit. In short, the size of the observable universe matters because it tells us where we come from, what we can know, and how small yet extraordinary our place is. It transforms the night sky into a story of beginnings, expansion, and possibility. It humbles us with our limits, yet uplifts us with the knowledge that we can glimpse the cosmos on scales that defy imagination. And it invites us to reflect. In a universe so vast, what does it mean to be human, to exist, to wonder? With that question lingering, we are ready to close our journey on the same note with which it began: wonder. For the observable universe, with all its immensity, is still only the beginning of what may exist, and contemplating it may be the most awe-inspiring act we can do. After all the numbers, analogies, and scientific explanations, we return to the original question: how big is the observable universe? The answer is both precise and overwhelming: about 93 billion light-years across, filled with at least 2 trillion galaxies and countless stars, planets, and cosmic wonders. But even as this figure sinks in, we must remember, this is only the observable part. Beyond our cosmic horizon lies a universe that is almost certainly far larger, perhaps infinite, extending into realms we can never see. That realization is where the true wonder lies. We have peered across billions of years of light, traced photons from the earliest moments after the Big Bang, and mapped a cosmos so immense that our words strain to capture it. And yet, all of that, the galaxies, the clusters, the filaments of cosmic web, is just a fraction of what exists. The observable universe is not the universe. It is only our window, shaped by time, light, and the expansion of space. There is something profoundly humbling about this. Every point of light in the night sky, every galaxy imaged by the Hubble or James Webb Space Telescope, is part of this observable bubble. But beyond that bubble are galaxies whose light will never reach us, hidden forever by the relentless stretching of space. The universe contains more than we will ever know, and yet what we do see is already enough to overwhelm our imagination. Standing beneath the stars, it's easy to feel small, but that smallness is not insignificant. On this tiny planet, orbiting one star in one galaxy among trillions, life has arisen that can look outward, ask questions, and begin to understand the cosmos. The fact that human beings, with all our limitations, can measure and describe a universe 93 billion light-years across is itself a kind of miracle. The universe is enormous, yes, but so too is our capacity for curiosity and wonder. And so, when we ask, how big is the observable universe? The answer is more than a number. It is an invitation to see ourselves as part of something unimaginably vast. An invitation to marvel at the strange fact that light carries stories from billions of years ago into our telescopes and our minds. An invitation to wonder what lies beyond the horizon in the hidden reaches of the cosmos we can never see. In the end, perhaps the most important truth is this: the universe is not just big, it is bigger than we can ever truly comprehend. And within it, we have glimpsed only a fraction. The observable universe is our window, our map, our story so far. But beyond it stretches a reality more immense than any number can capture, a reality that keeps us searching, questioning, and wondering. So as we close, let us hold on to that wonder. The stars above are not just lights in the sky, they are portals into an ocean of space and time. An ocean so vast that even 93 billion light-years is only the beginning. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.